All right, let's get started with our new unit. We are moving into Unit 12 now, which is Solutions, and we're going to start Unit 12 with a look at solubility. And solubility, we're going to look at this qualitatively. We'll come back and look at quantitative nature. Well, actually, we're going to do a little quantitative here too, but we'll look at it in more precision starting tomorrow. So to talk about solubility, we're going to talk about the three different kinds of solutions. And the first one is called a saturated solution. You've heard the word saturated before. And when it comes to solutions, what it means is that it has the maximum amount of solute. Now, the solute is the substance that's being dissolved. So you can think of this as the thing that's being acted on. And it's being dissolved in the solvent. And the solvent, we've seen solvents before, like water and hexane. And this is the thing that's doing the dissolving. And an important concept about a saturated solution is that it is at a given temperature. So this is going to be temperature dependent. We'll talk about that in a few minutes. So for a saturated solution, we actually are back into an equilibrium situation where the rate of dissolving, so if we draw a diagram here where we have our crystal, some crystal in the in the solution, the rate of dissolving coming out of the crystal has to be equal to the rate of crystallization. So in the solution now, we've got dissolved particles, and those particles we're going to recrystallize. And this is just like the vapor pressure situation where we had the rate of the one thing equaling the rate of the other. In this case, the rate of dissolving is equal to the rate of crystallizing. So because we're in an equilibrium situation, the concentration of the solute stays constant in the solution. And when we look at that concentration as a function of temperature, we get the curves that you see to the right, where each curve is a saturated solution for a different substance, and all different substances have the different saturated solutions. And the way we measure the saturation, or the way we measure solubility, is by measuring the maximum number of grams of solute that are being dissolved, that particular solute, in 100 grams of water. It's just a convenient way of making sure that we keep the amount of water always consistent, and that way we can compare how much of each solute does dissolve. By the way, this you'll find is chart F on your reference pack, and so you always have this available to you. So for the first question, the way we're going to use this chart is we're going to ask you to find the solubility of ammonium chloride at 80 degrees Celsius. So we come over to our plot, and we have 80 degrees Celsius at on the bottom on the temperature. And we're going to come up, we're going to find ammonium chloride. Here's ammonium chloride. So ammonium chloride is this line here, and it crosses 80 degrees Celsius right about there. Now remember, that's the saturation line. That's how much of the ammonium chloride will be dissolved in equilibrium at 80 degrees Celsius. And so that looks to me to be somewhere around 67 grams of ammonium chloride per 100 grams of water. Again, with these diagrams, if you're off by 1 or 2 in your reading, that's going to be okay. How about potassium chlorate? Potassium chlorate. Let's change colors. Potassium chlorate is this guy right here. And so at 80 degrees Celsius, as before, let's find out where the potassium chlorate crosses the 80 degree line. And it looks like it's crossing it at about 44 grams per 100 grams of water. All right, so we've got the concept of being able to find the saturation, being able to find the amount of dissolved solute at the saturated solution. Now, sometimes we're going to throw a little curveball at you. We like doing that, don't we? HCl, this is hydrochloric acid, it is in water, will be dissolved in a saturated solution containing 50 grams of water now. at 20 degrees C. Remember, we had 100 grams of water as our standard. So let's find our HCl right there, and 20 degrees right here. And so we come up that we will see that we could dissolve, it looks like about 72 grams in 100 grams of water. But we have to divide both of those by 2 because we have to divide the denominator by 2, and this is a ratio. So when we divide them both by 2, we're going to get about 36 grams. Let's put that up here. 36 grams of water of HCl in 50 grams of water. And we could also double the amount of water, and that would be something that you would be expected to solve as well. In fact, we may even have that on the homework. All right, so that's a saturated solution. Again, each line represents that saturated solution. Below the line, that means that more solute can be dissolved in the solution, again, at that temperature. Okay, so more solute can be dissolved. So we have, that's another way of putting it, is less solute than a saturated solution. Okay, we got less solute than a saturated solution, and that's a possibility as well. So let's take a look at A and B here, and two different situations. We've got KCl, 40 grams of KCl. Now, when we give you an amount of a solute, and you know what, let me change colors here so we can look at a different color. 40 grams of KCl in 100 grams of water, so we're back to the 100 grams at 60 degrees C. So when we give you a concentration and a temperature, you may not be on any particular line. So what I'm going to do is take 60 degrees C and 40 grams and find out where that intersection is. Notice I'm not on any line, but if I'm comparing this to KCl, here's my KCl line. The KCl line is up a little higher. We had 40 grams of KCl dissolved, but we could dissolve, the saturation is 45 grams per 100 grams of water. Because we're below that saturation line, it all dissolves. So all 40 grams is going to dissolve, and the resulting solution is unsaturated. We could put 5 more grams in at that particular temperature. All right, now sodium nitrate's all the way up high, and sodium nitrate line, the sodium nitrate line is this line, let's see, leave some room here. Here's the sodium nitrate line way up here, and if we're at 60 degrees C, then, I'm sorry, we wanted to be at 20 degrees C. So at 20 degrees C, we're back to 20 degrees C, and we're dissolving 100 grams of sodium nitrate. So come up to 100 grams. There's 100 grams of sodium nitrate at 20 degrees C. Now you can see that we're above the curve. There's the sodium nitrate curve. And so what this is telling us that since the saturation limit is 87 grams per 100 grams of water, and we have more than that, only 87 out of the 100 grams is going to dissolve. And what that's going to mean is that the remaining 13 grams, 100 minus 87, is 13 grams remain. 13 grams is undissolved, and it usually goes to the bottom of the beaker. This is a situation like trying to oversweeten tea or trying to put too much sugar in your iced tea. Once you put a certain amount of sugar in, putting any more sugar into your iced tea isn't going to dissolve anymore. All the rest of the sugar will just float to the bottom. And so that's a saturated solution. And I want you to realize that any time you have undissolved solute, undissolved solute is the case when you've got a saturated solution, because the solution now it's like a sponge that's completely full, saturated with water. There's another way of using that word. And so we have no more room for any more water to go in the sponge, so it just falls off to the side. Any questions you have, we will address in our classroom meeting. So now we get to a really interesting kind of solution, and that kind of solution is called a supersaturated solution, and they are super solutions, that's for sure. So a supersaturated solution is an unstable solution. It's unstable because it has more dissolved solute. More dissolved solute than a saturated solution should. And that puts us up above the line, up above the curve. But we don't just get there by trying to dissolve more solute than we can. Oh, by the way, again, at that temperature. These supersaturated solutions, because they're unstable, they can be disturbed. And when they become disturbed, we get a crystallization. We get a crystallizing, which we sometimes refer colloquially as crashing out. Crashing out of solution. So to disturb a supersaturated solution, there's a couple of things we could do. We can use a seed crystal. What a seed crystal is the same solute, but a solid form goes in there now. So you put a little crystal in there, and it gives the uncrystallized solute something to grab onto. You can shock the system. You can scratch the beaker. Who remembers scratching the flask, or scratching the flask? Who remembers scratching the flask when you when we were doing the aspirin lab, and that was trying to get any supersaturated aspirin out of solution? Or you can freeze it. And if you freeze it quickly, then you can also cause the supersaturated solution to crash out. Now, I'm going to insert here a video that's going to show you an example of a supersaturated solution and explain exactly what happens when it crashes out. Okay, so this is a supersaturated solution. It's a heat pack, or a reusable heat pack, that has a supersaturated solution of sodium acetate in it. And you can see it's a liquid. This would be a lot cooler in person, but we're going to do what we can do. So it's a liquid, and you can see that there's a little device inside there, a little clicker that you can click. And when I click that clicker, you can see the supersaturated solution becomes saturated. How do you know it's saturated? We have solid solute present. Now, the reason this is called a heat pack, and again, I wish you could feel this, but it is warm. And the warmth comes about because it's essentially retaining the heat that you use to dissolve it. You were breaking bonds, so you had to put some heat in to dissolve it. And when it forms the bonds, reforms the bonds of the solute coming together in the crystalline form, that alternating anions and cations, forming the bond releases that heat. It does renew. I can take this and I can put it into boiling water and it will renew again, and we can use it over and over again. And as you can see, it does say do not microwave. I have a feeling it would probably melt the plastic if we were to try to microwave it. Okay, that's cool, huh? But for now, let's go back to our supersaturated solution. Making supersaturated solution, as I said, is not going to be just like putting enough material in. So let's go back up to our top, and let's use potassium nitrate as our supersaturated solution. And let's suppose that we wanted to get a supersaturated solution of 130 grams of potassium nitrate at 20 degrees Celsius. So we're way up here, and we are well above, there's a saturation limit, well above the saturation limit for potassium nitrate. So because it takes energy to dissolve, it takes energy to split the bonds, what we're going to do is we are going to put the desired amount of solute into the system. As with our iced tea, it won't all dissolve, but then we're going to heat up the system so that we get it so that all of the solute dissolves. So if we go back up to the potassium nitrate, we would have to heat it up to above, let's see, 130 grams would dissolve here. So we've got to heat it up to above about 68 degrees C. Now, just to be careful, we're usually going to put these in boiling water, and that's what I do with my heat pack that we saw in the video. But then the trick here is once we've got all that dissolved, we're going to cool the system slowly and carefully. And when we cool the system slowly and carefully, what happens is the crystals can't organize, and the sodium acetate that we saw is a particularly large crystal, and it takes a lot of luck to get it to organize carefully. And so slowly and carefully, and so all the solute remains dissolved. There isn't anything, any solid solute in the system to give us a saturated solution. In fact, if we had the solid solute, we'd have been disturbing the crystal and disturbing the system of the seed crystal. So let's go back up to our diagram. And so we're going to cool this slowly and carefully. And now that we're carefully, oh, what happened? Erased my line. Slowly and carefully. And we're going to stay up above that system, up above that saturation line. Now, when we do crash it out, of course, it's going to come crashing down, and it's going to leave behind the 35 or so grams of solute that would remain dissolved. All right, let's take a look at some other things that have to do with solubility. If you've noticed, most of the materials up above, let's go back up here. Most of the materials increase in solubility as the temperature increases. And if you look carefully, you'll see that all of those materials are actually solids. They happen to be ionic solids in this case, but sugar, which is a molecular solid, also, and other molecular solids will also form this sort of thing. So sodium chloride, potassium chloride, I can just list all of them, potassium chlorate, etc., etc. How do I spell etc.? Sugar. All these will increase. The solubility goes up as the temperature goes up. And this has to do with entropy. So solid going to aqueous is higher disorder, and so is a higher entropy. and that higher entropy is going to give us a dissolving. As we saw with gases, anytime we mix things, we get a higher entropy. Let's go back up and let's take a look at what materials decrease in solubility as a function of temperature. And we've got SO2, we've got ammonia, and we've got, there's HCl again, decreasing in temperature. If you guessed that these things all have in common that they are gases, then you are correct. So gases, we had the HCl, we had the NH3, we had the SO2. We also have CO2, carbon dioxide. That will do the same thing. And the temperature, as the temperature goes up, the solubility goes down. And this also has to do with entropy, because when you have a gas as a solute, when you take that gas and you go to an aqueous, this is the only time when mixing decreases the entropy. It decreases the entropy. Gases have the highest entropy. And so nature favors, since we favor higher entropy as the temperature goes up. That means the gas comes out of solution. And you're going to reread part of the scuba diving article, because it's going to talk about, and we're going to see a little bit more about why we talked about it earlier, taking a hot shower is bad for you after scuba diving. Finally, another effect that gases have, and this only works for gases, is that as the pressure of a gas, and this is going to be the partial pressure of a gas, so as the pressure of a gas increases, its solubility also is going to increase. So part of the reason for this, more collisions with the liquid is more opportunity to dissolve. And again, referring back to the scuba diving article and what we talked about in class, essentially carbon dioxide in soda. Before opening, we're at about 5 atmospheres pressure. And all the CO2 is dissolved. By the way, that CO2, that's the actual partial pressure. The 5 atmospheres is the partial pressure of the carbon dioxide. And then after you open it, the pressure of the CO2 comes way, way down. It's probably on the order of about 1% of the atmosphere. And so when you open it, the pressure of the carbon dioxide goes down, the solubility goes way down, and the bubbles form. All right, so this is called Henry's law, and we're only going to look at it qualitatively. But it is a direct relationship, a one-to-one relationship. So if the pressure doubles, then the solubility will also double. All right, so we are done with solutions and solubility curves for now. And our next look, we're going to see how to quantify some of the solute in solution, so that we can then in the following day look at it stoichiometrically. I know you're all excited about that. All right, so I will see you in our class session, and I hope you're all doing well.